Welcome back. Now on the screen display is a picture showing a roof of a building. What is the shape of that roof? Is it a cuboid? Is it a cube? Is it a sphere, or is it a cylinder, or is it a pyramid? Are you able to identify the shape of the roof? Definitely you can. This roof is a pyramid. It takes the shape of a pyramid, and a pyramid is a polyhedron that has a base, which can be of any polygon and 3 or more triangular faces that meet at a point called the apex. These triangular sides are sometimes called the lateral faces to distinguish them from the base. Now, here is a pyramid. You can see there are triangular faces which meet at V, and V is the apex, the topmost point from the base. And you can also see the base of a pyramid. The base can be any polygon. It can be a square, a rectangle, a triangle, a pentagon. And for that matter, because all pyramids will have triangular faces which are slanting, but the bases may vary, and therefore pyramids are named by the shapes of their bases. If a pyramid rests on a square base, we call it a square-based pyramid. If it rests on a triangular base, we call it a triangular pyramid, and so forth and so on. Now, in a pyramid, we have these slanting edges, the slanting edges, and the lateral faces, the faces which are slanting. In this case, they are always triangular. A pyramid also has altitude, or the height. The height is the vertical distance from V to the base, and in this case, it is VO, the vertical distance. Sometimes a pyramid will have all the slanting edges equal, like in this case, VB, VC, VD, VA are all equal. In this pyramid, all the slanting edges are equal, and if we have all the slanting edges being equal, then that pyramid is called a right pyramid. So in a right pyramid, all the slanting edges are equal, and when you have any pyramid, look at the slanting edges. If the slanting edges are equal, then definitely it is a right pyramid. Now, this is a right pyramid because all the slanting edges are equal. Now, something special about a right pyramid, the altitude of the pyramid, that is VO, will always meet the base at the center. And that will only happen if the slanting edges are equal. It only happens in the case of a right pyramid. The altitude VO will always hit the base at the center. Right. Now, on the other hand, we have an oblique pyramid. This one here is an oblique pyramid. An oblique pyramid, unlike a right pyramid, the slanting edges are not equal. Now, the slanting edges here are VD, VC, VA, and VB. Those are the slanting edges. If you look at them, you'll clearly see that they are not equal. So where the slanting edges are not equal, we have an oblique pyramid. Now, where is the altitude of this oblique pyramid? The altitude, the altitude is the vertical distance from V to the base. Is it VO or is it VA? The altitude or the height of this pyramid will be VA here, this one here, because this is the vertical distance. It is not VO, right? It's not VO. So in an oblique pyramid, if you draw a line from V to the center of the base, that line will not be vertical. Will not be vertical. And that is another way of identifying an oblique pyramid. You try to draw a line from V to the center of the base. If that line is not vertical, then that pyramid is not right pyramid. It is oblique. And that happens because the slanting edges are not equal. look at the right pyramid again. In the right pyramid, you can see clearly the edges, the slanting edges are equal, and therefore the line from V to the center of the base is vertical, and that becomes the altitude. The height of the pyramid is always within the pyramid, and it actually hits the base at O, where O is the center of the base. Most important, in a right pyramid, all the slanting edges are equal, and in an oblique pyramid like in this one here, the slanting edges are not equal. Now, if you look around your environment, you'll see lots and lots of objects which are in the shape of a pyramid. Most roofs are in the shape of a pyramid, like what we have in our picture. We can look at more of those pictures. This is a roof which is in the shape of a pyramid. We have another one, all right, and so forth and so on. There are very many. Even a milk packet is actually a pyramid sitting on a triangular base. So this is a triangular based pyramid. We also have a tent, and we have the Egyptian pyramids where pharaohs were buried. You know, sometimes in your history, when you talk about pyramids, someone thinks about the Egyptian pyramids. Now, we are going to use to discuss a question, and that question will be based on a pyramid. That is why I thought it important to introduce and explain to you what is a pyramid. So get ready for the question, and have your calculator ready, and have your pen, and also remind yourself of what we discussed earlier, how to calculate the length of a line in a three-dimensional object, and also how to calculate the angle between two lines in a three-dimensional object. All right. Now, in your exercise book, draw the pyramid displayed on the screen. In your exercise book, draw the pyramid displayed on the screen. You can pause the video as you draw the pyramid. Okay. After drawing the pyramid, please copy down this question. The figure above shows a right pyramid with apex V and base ABCD. Given that the height of the pyramid VO equals to 7 centimeters, AB equals to 6 centimeters, and AD equals to 5 centimeters, and that M is the midpoint of AB, calculate the length of line BD, slant edge DV, line DM, and line VM. Then part B, calculates the angle between the lines VD and DB, VM and OM, VD and DN. You can pause the video as you copy the question. Now, this question is a follow-up to the concepts we learned earlier. Remember, or you will recall that in our lesson 1 and lesson 2, we covered the concept of calculating the length of a line in 3D, and also the concept of calculating the angle between two lines in 3D. This question will help you practice those two concepts, or those two skills, which are very important even as we plan to scale up the topic. And therefore, as a follow-up question, I expect you to attempt it first. So after drawing the pyramid and copying the question, please settle down and try this question. I'm saying after copying the question and drawing the pyramid, settle down and attempt this question. It is important that you attempt before we go through the solution. It's very important. It will give you an opportunity to check whether you understood the concept of calculating the length of a line in 3D, and also the concept of calculating the angle between two lines in a 3D object. Okay. Good luck as you begin to do the question. Okay, welcome back. I hope you've had a good time attempting the question and believing that you've done the right things. I would like us to go through the correct working to give you an opportunity to compare your work with my work, and just be sure that you did the correct thing. All right. Now, question A, Roman 1, requires us to calculate the length of BD. We look at our 3D setup or 3D drawing, and we can identify BD is a line running from B to D, and ask ourselves, or look at the 3D and identify the plane figure on which BD lies. Clearly, BD is running on the base, so it is a line on the base ABCD. The next thing is to look at that base and ask ourselves what is the exact shape of that base. That base is a rectangle. If you look at the 3D drawing, you might not see that rectangular shape, because in most cases drawings in 3D do not reflect the exact shape. So we understand three-dimensional drawings from the real objects which the 3D represents. This is a pyramid, and at the back of our mind I would like us to have the real pyramid, and we will be able to understand that ABCD on which BD is lying is a rectangle. So we will draw that rectangle separately, and here we have it. Clearly, we bring in the dimensions of the rectangle. AB is 6 and AD is 5. Clearly, BD is the diagonal. So we are good to go, and here is the working, and we calculate the length of the diagonal BD, and because this is a right angle triangle, we apply Pythagoras Theorem in calculating the length of BD. So BD squared equals to AB squared plus AD squared. We bring in the values, and we have 6 squared plus 5 squared equals to 61, and so BD equals to the square root of 61, and once again we use our calculator to get the square root of 61 as 7.810. so BD is 7.810, and that is the diagonal of the base, right? I hope you got it right. All right, okay. Next we move to Roman 2, which requires us to get the length of DV. So you get it ready. Now, welcome back. We look at the calculation of DV. We move to our three-dimensional drawing of a pyramid, and we can identify DV. DV is one of the slanting edges of our pyramid. The next thing is to look at the pyramid keenly and identify the plane figure on which DV lies. We need to identify the plane figure within the pyramid on which DV lies. In the pyramid, there are several plane figures, you know. We have the base as a plane figure, we have DAV as a plane figure, we have ABV as a plane figure, we have several plane figures within this pyramid. So which of those plane figures, which of those plane figures contains DV? You know, look at it keenly. I hope you can see clearly that DV lies on triangle DVB, right? Well, we can also use DV as part of triangle DVB. You know, there are several scenarios. There are several of them, but I have decided to pick out triangle DVB. So we pick out that triangle and draw it separately. But before we do that, we need to understand what type of a triangle is it. clearly dv equals to vb because both of them are slanting edges of the pyramid. This is a right pyramid, and therefore all the slanting edges are equal. That is to say, vd and vb will be equal. And so, what does that mean? It means that triangle DVB is an isosceles triangle, so we will draw it separately and exactly as an isosceles triangle. Okay, so here we have it, and we can bring in the dimensions. We know that VO is the height of our pyramid, so it is 7, and also DB is 7.810, having been calculated in part A Roman 1. And so the stage is set, and we do further analysis, and we extract another triangle from this isosceles triangle. We bring out triangle VOD. VD equals to VB, and therefore if VO is vertical, it means O is the midpoint of DB. So we can get the length of DO as a half of 7.810, and so our DO is 3.905, and that sets this triangle, ready to be used in the calculation of DV. In this right angle triangle, DV is the hypotenuse, so we can aptly apply Pythagoras Theorem. DV squared equals to DO squared plus OV squared. We bring in the values, and we have 3.905 squared plus 7 squared equals to 64.25. DV is the square root of 64.25, and from our calculators we get DV as 8.016. Okay, that means that VD is 8.016. Because this is the right pyramid, it therefore follows that all the other slanting edges have a length of 8.016. Okay, I hope you got it right. In case you didn't, go through the working so that you can be able to see which step you missed. But if you got it right, well done. Next, A Roman 3, we are required to calculate the length of DM. Once again, we come to our diagram and our 3D drawing, and we can identify line DM. All right, M is a point on AB such that M is the midpoint. Now, the next question is to identify the plane figure on which DM lies. Once again, DM lies on the base, and so we will extract the base and draw it separately. But before we do that, we need to understand what is the shape of ABCD. Now, ABCD is clearly a rectangle, and so we're going to draw a rectangle separately, not what we are seeing in the 3D. In the 3D, we are seeing ABCD as a parallelogram. We shall not draw a parallelogram because that is a confusion that normally comes when you look at three-dimensional drawings. It's very common. That's why I said earlier that it is important to look at the pyramid and understand it from the real object. You keep referring to the real object in your mind, So if you look at the real pyramid, you realize that ABCD is not what it seems to be on the drawing, but it is a rectangle. So we draw a rectangle, and we can see point M is lying on AB as the midpoint, and so this is line DM. And so if you know AB as 6 and M is the midpoint, I believe you are able to work out the length of AM. DA is 5, and so the stage is set, and here we are. AM is 3 and DA is 5, and once again we can pick out right angle triangle DAM, and in that right angle triangle you realize that DM is the hypotenuse. Pretty simple. Everything comes down to right angle triangles, and we'll always once again apply Pythagoras Theorem, and we have DM squared equals to am squared plus ad squared, that is bringing the values, and we have 3 squared plus 5 squared gives us 34. So dm is the square root of 34, and our dm is nothing but 5.831. You know, it's pretty simple. Okay, it's pretty simple. All right. Finally, we look at Roman 4, where we are required to calculate the length of VM. Once again, in our diagram, you can see VM. VM is actually the slant height on this face. Remember, VB are called slanting edges, but if you take one of the triangular faces and get its height, we call that one slanting height. Okay, so VM is the slant height on this triangle here. Okay, so we are supposed to get the length of that slant height. Now we need to identify the triangle, the plane figure on which VM lies. There are several scenarios, but I've decided to see VM as part of triangle VMO. Okay, you can see triangle VMO. That is the triangle I have drawn separately here. VMO. VM is part of triangle VMO. So we draw triangle VMO separately, and here we have it. And you know, if you look at MO, MO is actually running on the base, it's horizontal, and VO is vertical, and therefore this is a right angle triangle at O. Now, O is the center, you know, is the midpoint of the base, is the center of the base rather. And so, what is the length of MO? We know AD is 5, and clearly MO will be a half of 5, because AD is 5, and therefore all the way from M through to the other side is also 5. And that means O is the midpoint, so MO is a half of 5. Okay, and again, VO is the altitude of our pyramid, so VO is 7, and MO is a half of 5, which is 2.5, and that sets the stage, you know, for the calculation of VM. So we have right angle triangle VMO, and VM is the hypotenuse. So we apply Pythagoras Theorem as VM squared equals to OM squared plus OV squared. We bring in the values, and we have 2.5 squared plus 7 squared equals to 55.25. So VM is the square root of 55.25, and that gives us 7.433 as the length of VM. All right. Let us look at an alternative analysis. Suppose you decide to use to see VM as part of triangle VAB. Okay, so this is what we have. You can see VM is part of triangle VAB. Now M is the midpoint, so M is the midpoint of AB. That means VM is perpendicular to AB, because VA and VB are equal. If VA and VB are equal, that is, we have an isosceles triangle, and you drop a line from the apex to the center of the base, such line will always be perpendicular to the base. So VM is perpendicular to AB, that is to say, we have right angle at M. Okay, so that sets the stage, as we can see here. The stage is set. Clearly, the stage is set. Let us. Okay, so here is our triangle VAB. We know VA as 8.016, because that is a slanting edge, and AB is 6 centimeters, and if M is the midpoint, that means AM is 3 centimeters. So we can use a right angle triangle VMA. Okay, so VMA is what we shall use. We know the hypotenuse as 8.016, and we know the one of the shorter sides here as 3. So we can apply Pythagoras Theorem that VM squared equals to AV squared subtract AM squared. Bring in the values, we have 8.016 squared minus 3 squared, and that means VM squared is 55.26. We get the square root of 55.26. Once again, we end up getting VM as 7.433, the same as what we got before. So there are two different approaches, as long as your analysis is accurate. And so far so good. We have calculated the lengths of the lines as required in part A of the question. So we move to part B, which requires us to calculate the angles between various lines within the 3D. Okay. Now, part B Roman 1 requires us to get the angle between line VD and BD. Okay, we look at our 3D and we can see both lines VD and DB. Look through keenly and identify the point at which VD and DB intersect. Now the next thing is to pick a plane figure which contains both VD and DB. That is triangle VDB. That is the triangle we shall draw separately. So we can see VD and DB, and clearly we know that VD equals to VB. That means the triangle drawn is isosceles. You know why VB and VD are equal. They are the slanting edges of our pyramid. Now, so the angle required is the angle VDB. The line VD and DB meet at D. So the angle between them is the angle VDB. So we are supposed to find the value of angle VDB. So that sets the stage, and here we are. So VD is 8.016, and the entire of DB, you know, I think is 7.810, and the height VO is 7. Remember, VO is perpendicular to DB, and O is the midpoint of DB. Now, we want angle theta, and we pick the right angle triangle VOD. So sine theta is 7 over 8.016, and that is 0.8733. So theta is the sine inverse of 0.8733, and the angle required is 60.84 from your calculator. Okay, that is it's fairly simple. Okay, it's fairly simple. Next, we would like to look at the angle between VM and MO. Once again, we pick the plane figure on which VM and MO lie. So VM and MO are sides of triangle VMO. So we will extract and draw triangle VMO. And so we want the angle between VM and MO. The angle is clearly angle VMO, and the triangle VMO is the right angle at O, because VO is the vertical height of the pyramid and MO is on the base, meaning MO is horizontal. So if this is vertical and this is horizontal, that means the angle at O is 90 degrees. So we have a right angle triangle, and we would like to find the angle VMO. So that sets the stage, and here we are. And the angle we want is marked alpha. So VMO is the angle we want, is marked alpha. And once again, we have VO as 7 centimeters and VM as 7.433. And we can apply sine ratio. So sine alpha is 7 over 7.433. Sine alpha equals 0.9417. And alpha is sine inverse of 0.9417. And therefore our alpha is 70.34. That is the angle between VM and OM. Okay, it's pretty simple, and In this part, it appears you have to remember how to apply the trigonometric ratios in the context of a right angled triangle. Lastly, we look at one 3, that is the angle between VD and VD and DM, sorry. Okay, let us analyze the angle between VD and DM. So once again, we are required to pick out the plane figure on which both VD and DM lie. Clearly, VD and DM are part of sides of triangle VDM. So we will draw separately triangle VDM, and here we have it. And we can see again VD and DM, and from this triangle you can see the angle at which VD and DM intersect. They intersect at angle VDM. So here is a triangle whose dimensions we can fix, because DM we have calculated as 5.831. We know DV as 8.016, and also we know VM as 7.433. This is not a right angle triangle, and it's not isosceles, it's a scalene. And to find angle theta, we apply Cosine Rule. And here we have it. And so cos theta, if you evaluate this using our calculator, we get 0.4601, and our theta is the cosine inverse of 0.4601, and that gives us 62.61 as the angle between VD and DM. So throughout the question, you realize that concept of calculating the length of a line in 3D, the concept of calculating the angle between two lines in 3D, after all, is not difficult. It's very simple. All you have to do is to be interested, to like what you're doing, and to do a lot of practice to be able to be good at it. So in our next lesson we shall scale up and bring in the concept of projection of a line on a plane, because ultimately we look at the angle between a line and a plane, angle between two planes, and angle between skew lines. But before we come there, it's important that you master these basics of calculating the length of a line in 3D. You also should be well grounded when it comes to calculating the angle between two lines. Okay, and till then, thank you for attending the lesson.